right, so I'm going to start with a couple of definitions. These are the words squeaky as chairs. So, first order.
You break it.
Differential equations. And one can write them this way: dy dx is some function of x and y, and one can always write the function of x and y as a ratio of two other functions of x and y. And then what one has is a system p of x and y dx plus q of x and y dy equals 0. And this is called a first order ordinary differential equation. Now, what one can, there's a special class of first order ordinary partial, first order ordinary differential equations that's easy to solve, and these are the ones that are separated. They're separable. So, the separable case is the one you've learned to love. In this case, separable looks like this. If this is your equation, then the variables are already separated. And then you can just integrate. You get 0 is the integral up to x of f of x prime dx plus an integral up to y of g of y prime dy prime, and this is dx prime. And this is an equation for y of x. So in other words, this is an equation. 0 equals this integral plus that integral, and that gives you an equation for y of x. This is called a general integral. I'm skipping the next few examples because we did them in the problems course. The next topic is, as you might expect, when you get most by the way, this thing is called a general integral. When you have most first order ordinary differential equations, they may be separable, but it's not obvious at first glance. That's called hidden separability. Okay, hidden separability. So for example, suppose these functions, in other words, what we have is 0 equals, suppose they're of a special form. U of x, v of y, dx plus r of x, s of y, dy. So suppose that's your equation. That is to say that p and q factorize into functions of x and y. Then what you do is you just divide by v of y times r of x, and you get the equation u of x over r of x dx plus s of y over v of y dy equals 0, and now this is separated. You integrate like this, and you get an equation y of x. Maybe I will do an example of this. All right, let's look at this. X, y squared minus 1, dx minus y, x squared minus 1, dy. Let's say 0 is equal to that. Well, we divide by y squared minus 1 times x squared minus 1. And what we get is 0 equals x over x squared minus 1 dx minus y over y squared minus 1 dy. Separated, you integrate, and you get log of x squared minus 1. So 0 equals log of x squared minus 1 minus log of y squared minus 1. And that's equal to some constant minus log c, because after all, when you do an integral, there's always a constant of integration somewhere. And so what this tells you is that the log of x squared minus 1 over y squared minus 1 is some constant d, say, and consequently, basically, x squared minus 1 is equal to y squared minus 1 times some other constant, let us say e, and you can finally form, solve for it exactly. You get the square root of 1 plus, well, let's see. Let's cancel the e there and make this a c. And so then what we have is y squared is equal to 1 plus c x squared minus 1. And when you take the square root of that, you get c x squared minus 1. So that's how that's an example of hidden separability. What you may have noticed is something that's always true of differential equations, namely that the subject is much less systematic than complex variable theory or linear algebra or Fourier transforms. It's you have a differential equation, any way of solving it is fine. And as you vary the differential equation, there are different ways of solving the differential equation. Okay, let's now look at exact differential equations. So for example, 0 is p of x, y, dx plus q of x, y, dy. Suppose that's our differential equation. When is it exact? It's exact if this thing is the differential of some function phi of x and y. That d that gives us the differential is also called the exterior derivative. And it's part of the algebra of forms. And it's the easy part of the algebra of forms. And so, of course, d phi is just phi sub x dx plus phi sub y dy. And if this is the case, then the differential equation is exact, if you can write it this way. So you see, here you have two different functions that are in principle unrelated. Here you have x and y derivatives of the same function. If you can write it this way, it's exact. And so how do you know if you have something like that it's exact? Well, p has to be the x derivative of some function, and q has to be the y derivative of some function. But then you know that the y derivative of p is phi xy. That's the same thing as phi yx, but that is the x derivative of q. So the criterion of exactness is that partial P, partial Y should equal partial Q, partial X. That's the deal. If that's the case, then the thing is exact. Okay, and this thing is, if the differential equation is exact, then it's easy, or at least possible, to integrate it, and this thing is therefore called the condition of integrability. Condition of integrability. And an example, a very simple example, is an example that's already separated. Well, this one is p sub y is 0, and so is q sub x, so the thing is trivially exact. An example of an exact differential is p dv plus v dp equals 0. Well, that's just equal to d of PV, pressure volume, okay? And so that's exact, and so you can integrate, and you then get PV equals a constant, and the constant in this case is number of molecules, Boltzmann's constant, absolute temperature. By the way, let me just insert here the van der Waals correction to this formula, which was actually in his PhD thesis. And it was P plus N over V squared alpha prime times V minus N P prime equals NKT. And so what you imagine here is that there's some excluded volume. So B is the volume of each, the average volume of each molecule. And over here, the alpha prime is the mutual attraction of the molecules for each other. And the basic lesson, which actually I don't think we get taught this in typical classes, but imagine vacuum, okay? Molecule, molecule, two neutral molecules. They always attract. And the reason they attract is that they know that if they rearrange their electrons, they can create two dipoles suitably oriented that attract. That's one way of thinking about it. There are other ways of thinking about it. So if you have two neutral molecules in the vacuum, they attract. The force is something like 1 over r to the 6th, unless they're far apart. And then it turns out it's 1 over r to the 7th. So, just something. So, by the way, this formula of van der Waals was one hint that the chemists were right in the 19th century when they were talking about molecules. You know, you can say 2NaCl plus whatever, 3HCl or whatever, and you balance the equation, and that when chemists were doing that, some physicists made fun of them and said that they were talking about things that didn't exist, but turned out the chemists were right. And one of the breakthroughs, apart from this, was Einstein's relation that the viscous friction coefficient times the diffusion constant actually is kT. These two things could be measured, and of course the temperature can be measured. that allowed people to calculate Boltzmann's constant. And and once they knew what Boltzmann constant was, they knew what n was. And once they knew what n was and what P and V were, or if they just weighed the volume of gas, they could find out then what the mass was of each molecule. So this relation led to, just related to Brownian motion, led to...
How do you measure those parameters?
How do you measure what?
The diffusion and the other parameters.
Well, all right. Well, diffusion is, you know, you've got a beaker, say, of water, and you put some colored solution in one place, and you time how long it takes for the whole thing to turn blue or whatever. I mean, that's a theorist's way of doing the measurement, but there are better ways. This thing, you know, you just see how you calculate, or you see how slowly, how much drag there is on the motion of the fluid through itself, or a particle through the fluid. This is discussed a little bit further on in, I don't know, the chapter on probability and statistics, I think, goes into such things a little bit. It's part of biophysics, and my interest in that field cooled when the university fired one of our assistant professors who was going through a divorce and doing some very good research, but his idea of publishing was creating a marvelous website that was universally accessible rather than putting things in journals. Oh well. All right, let me just, let's just give you one more example. Population growth, one equation is dn over n squared is dt over b. This b is not the same as b prime. You can integrate that and you get n of t equals b over t minus little t. Turns out that this works if you set big T equal to 2025 and b equal to 2 10 to the 11 years. This actually is fairly good for the period 1 through 1970. In other words, the year 1 through 1970.
You know, like human population growth?
Yeah, we're talking people, yeah. Notice 1970 was where it stopped. I think maybe that was when the pill became cheap, widely accessible. Anyway. Okay, meaning of exactness. All right, suppose you have, once again, d of x and y, dx plus q of x and y, dy equal to 0. You can always integrate this. And you might say, well, is this, you want this to be 0, is this also d phi? And so you might say, well, I can also always kind of make this d phi if we just define a function phi of x and y, comma, a contour x0, y0 as an integral from x0, y0 to xy along some contour c of p and x prime, y prime, dx prime plus q of x prime, y prime, and y prime. So this gives you something that satisfies this equation, but the trouble is the phi isn't a function of x and y, it's a function of the contour as well. And the condition that phi be independent of the contour is the condition of exactness. So in other words, if there's some, how should I say, if you can write an actual function of x and y as p dx plus q dy, then the integral along any curve is independent of the curve, because the integral of p dx plus q dy is just phi of x and y minus phi of x0, y0, if you're going from x0, y0 to xy. So in other words, if this thing is actually the differential of p, then this is the integral of d phi. And then you actually get a relation. And in fact, if d phi is 0, then this is equal to 0, and this is an equation for y of x. Yes?
I have a question. In the top equation where you first introduce phi as a function of x,
The
y,
top
y,
equation.
No, the one right beneath that.
This
yeah,
equation.
that guy. Yeah, so you have limits like from x0, y0 to xy, but it's like you're only doing one integral along x and one integral along y. It's
Right,
like,
but
and
as
that
you go
kind
along x, y prime is a
it's
function of x.
constrained, okay.
A function of x prime, yeah.
Okay, sure. So it's really like you're doing one integral over x and you're doing one integral over
Yeah,
or
but
y.
these are
But the-
integrals along contours.
Okay, sure.
It's like in C complex variables.
Yeah, sure.
And, all right, so I've got to pass out some candy here. Mr. E. Good. What's your name again?
Austin?
Austin. I have a son who lives in Austin.
Yeah.
Not inside from the city.
Yeah, sure.
People who live in Austin say they don't live in Texas, they live in Austin.
Yeah. I had a lot of brothers who lived there.
Okay, there are two examples. I think I'll skip the first one because it's so abstract that, the last thing you want of an example is to be abstract. You want the example to be concrete. So I'm going to do the second example, and I would skip the examples and put them in the problem section, but some examples, we need some examples. Okay, so suppose our equation is p of x and y dx plus q of x and y dy. And in this case, it's log y squared plus 1 dx plus 2y x minus 1 y squared plus 1 dy equals 0. Okay. Now you can look at that and you can say, well, that's got hidden separability. Because if you divide by the log times x minus 1, you can separate. You can also check that it's separable, or that it's in fact exact. So A, it's got hidden separability, but B, it's already exact because the y derivative of P is 2y over y squared plus 1, and that's equal to the x derivative of Q, which is 2y over y squared plus 1. Okay. So you know it's exact. And of course, the simple way of solving this thing is to just use the tricks that I illustrated back there for separable differential, hidden separability. But suppose instead we just want to just use the exactness and that'll be related to this business of contour integration. So what we can do is we can say, we can define the function phi of x and y as an integral of this one, which is p dx, and this will then be the integral of p plus some unknown function of y. And so the integral of p is the integral of log y squared plus 1 dx plus c of y. Well, this is a pretty trivial integral here. This is, notice that this is y squared, not y prime. And so this is log y squared plus 1 just times x plus c of y. Okay, so that gives us a formula for phi, but in terms of an unknown function c. On the other hand, if we now take the y derivative of phi, what we get is first from here we get 2xy over y squared plus 1 plus the y derivative of c, but this is an unknown function. On the other hand, this thing is q sub x. So what we do is we set this equal to q, I should say. This is equal to q, which is equal to 2y x minus 1 over y squared plus 1. So in other words, this thing is p, and this, of course, is q, and the idea is that phi sub y is p, phi sub x is q.
I have a question.
No, wait a minute, that's phi sub y. Phi sub, all right, I screwed up. Hold on.
Should it be q sub x? Should that be the x derivative of q? Because we're taking the y derivative. Why are we
P-
equal to q?
Yeah, you know, I think you're absolutely right. P, this is actually the x derivative. And q is phi sub y. And the condition of exactness is that p sub y is equal to q sub x. Okay. So, anyway, we're at this stage, and this gives us a formula for c. And it says c sub y is minus 2y over y squared plus 1. We can integrate that to c of y is equal to minus log of y squared plus 1 plus some constant of integration d. Now we can go back to the original equation here, which was that phi of x and y was x log y squared plus 1 minus, so that's this term plus c, and c is this term. So this is minus log y squared plus 1 plus d. And so this, of course, is just x minus 1 times log of y squared plus 1 plus d. And now we can set this equal to constant e, because the statement, the differential equation is d phi is 0. So phi is a constant. And so that just tells us that if we just subtract d from both sides and call it f, some other constant, this is our solution. And you can then unravel that to y of x is equal to square root of e to the f over x minus 1 minus 1. Well, that's sort of a curious actual result there. All right, let me back here for a shot of water and another piece of chalk. Okay, now, so if the differential equation is exact, then you can solve it in principle. It turns out that if one is lucky or clever, one can find an integrating factor that makes the differential equation exact. So the integrating factor we call alpha. So we have alpha p dx plus alpha q dy 0, and in fact is not simply a 0, but we're going to say that this is d phi. So that means that alpha p is phi sub x, and alpha q is the y derivative of phi. And then alpha p, the y derivative of alpha p, is phi of xy, and that has to be the x derivative of alpha q. So that's the condition of, what the integration factor has to do. The integration factor has to be such that alpha p, the y derivative of alpha p, is the x derivative of alpha q. Okay, and there are a gazillion examples of this. For example, if you have y dx minus x dy equals 0, well, that in fact has hidden separability. You just divide by xy. But another possibility is to say, well, alpha is just 1 over x squared. So that gives us the equation y over x squared dx minus dy over x equals 0. So now, alpha p, what do we want? We want the y derivative of alpha p. Well, alpha p is the y derivative of y over x squared, and that's just 1 over x squared. On the other hand, we want that to be the x derivative of alpha q. Well, alpha q is minus 1 over x, and the x derivative of that is 1 over x squared. So you see, these two are equal. So this is an example of an integrating factor. All right. So, there are just, a gazillion tricks. All right, let me now change topics a little bit. Something that comes up in physics, and so it's an example of differential equations, but it's an issue that comes up in physics. Okay. Suppose we have f of x is f of x1, x2. Let's see, how many we have? We have k of them. All right. Suppose f of tx, which is to say f of tx1, tx2, txk, is t to the n f of x. Then what we say is that f is homogeneous, and we say homogeneous of degree n, that exponent. Okay, and a simple example is, suppose f of x, y, z is equal to z squared log of x over y. Well, that's homogeneous of degree 2, because if you multiply them all by t, the t cancels here, but it comes out as t squared here. So that's just an example. Now, Euler never wanted to sit idle. Derived a theorem for functions that are homogeneous of degree n. And what he did was he said, let's just take d by dt of f of tx. Well, if we differentiate this form, it's trivial. It's n t to the n minus 1 f of x. On the other hand, if we differentiate this form, then it's a sum. So you differentiate f of tx1 dot 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 txk, partial with respect to txi, I equals 1 to k, and then you take the derivative of txi with respect to t. So that's another way of doing the derivative. And of course, the first part is trivial. This is a sum, I equals 1 to k, of xi times this derivative, which is now, I can write it as just tx if you want, partial txi. But now the clever thing is that Euler said, okay, let's look at this equation for, let's set t equal to 1. Setting t equal to 1, we have n f of x equals, and now this sum is much simpler. It's a sum I equals 1 to k, xi partial f partial xi. So that's the general result. And I'll just write his name here, Euler. Imagine that near Houston, this is sometimes written this way, but it's a very cute and useful theorem. And so let's see now, which of these examples should I do? Maybe I will do the first one. All right, internal energy U. If you multiply the entropy by T, the volume by T, and the number of particles by T, you just made the system bigger by T. And so if you increase the internal energy by SVN, at least if the system is at all reasonable, that's the way it is. And what can you conclude from that? Well, you can conclude that, let's see, how do I want to say this? The temperature is defined as partial U, partial S, constant V and N. Pressure is minus partial internal energy, partial volume, constant entropy, number of particles. jth chemical potential is partial U, partial number of particles of that kind with SV and I not equal to J constant. Okay. So these are just definitions of thermodynamic quantities. And so now what do we have? We have that the change in the internal energy is TdS minus PdB plus the sum UJ dNJ. On the other hand, Euler's theorem tells us that it's homogeneous of degree 1, so homog n equals 1, and that tells us that U is equal to a sum of the independent variables times the derivatives. And so that would be then, let me get this right, the independent variables are S, V, and N, so it's partial U, partial S times S. In fact, I don't need the sum thing, let me just write this as plus P partial U partial V plus, now I do need the sum, it would be partial U partial NJ, and it would be NJ. And now, using these definitions, we see that partial U partial S is T, so this is TS. P is partial V partial U is minus, I shouldn't have put a P here, I should have had a V. And partial U partial V is minus P, so this is minus PV. And then this one is mu J, so it's the sum mu J NJ. And once we write things like that, then we see, oh, now it's obvious that U is homogeneous of degree n, because if we multiply S, V, and N all by T, U just increases by a factor of T. By the way, there's something in here that you want to notice, namely that pressure is defined as minus the change in the internal energy with respect to a change in volume. Okay, so now we think about the universe. We suppose there's an energy density of the universe, of empty space, and suppose that that energy density is some small positive number. If we increase the volume, the internal energy goes up. But that means that the pressure, that this is positive, so the pressure is negative. It's that negative pressure that accelerates the expansion of the universe. That's what we call dark energy. What we call, or what we don't understand, of course, except in this sense. So, well, I don't know. I think the rest of the example I'll just leave for you to read, if you want to read it. There. Okay, and I'll go instead to the Virial Theorem. Okay. This is really important in physics. And it's an application of Euler's formula here. And I'm going to discuss it non-relativistically. It's presumably a relativistic version, but I'm just going to do the non-relativistic version. Okay, first of all, what's the virial? Well, for a system of n particles in three-dimensional space, it's a sum I equals 1 to 3n of xi pi. So xi is the ith coordinate of the, in other words, x1 is the x coordinate of the first particle, x2 is the y coordinate of the first particle, x3 is the z coordinate of the first particle, x4 is the x coordinate of the second particle, and so forth. All right. So this is the virial. What's the time derivative of the virial? Well, that's g dot, and that will be a sum. Well, x dot is just b sub I. And then pi. Well, pi is the force, the ith force. In other words, Fi. Okay. On the other hand, non-relativistically, T is V1 P1 plus dot 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 Vn, that's V, Pn, all that over 2. P being mv, so you have mv squared over 2 and so forth. So this thing is twice the kinetic energy of the system plus a sum xi, the ith force, I equals 1, 3n. Okay, now here comes a physical assumption. The physical assumption is we're considering the virial for a system of particles that are bound. Okay, so for example, all the particles in the solar system, not counting that crazy thing that came from another solar system and shot down and fortunately missed the Earth, or we wouldn't be here. By now has as far away from us as Jupiter, at least. I don't know. Maybe somebody here has the latest astronomical data. I don't know. There's a cute graphic in the New York Times about this. Okay, well, if these things are bound, then the virial is essentially bound. That is to say, the x coordinates are limited to some, they don't get any farther out than Uranus or whatever, or Neptune, say, if we're talking about the solar system. And the momenta have to be finite because otherwise the system would be unbound.
Okay. In your expression for T, should the subscript on the final Pn be 3n? Or
Absolutely. Yes, of course, 3n. All right, so you get 2 candies.
that's a
Huh?
I think this is
You don't want them?
okay, yeah.
I mean, you're entitled.
I don't want to interrupt.
Brush your teeth. All right, here, let me toss them to you. Oh, shit. All right, I'll throw this one over. All right, good. All right, so if G is bounded, then the time average of G will be G at some huge time minus G of 0 divided by some huge time. We now let the huge time go to infinity, so this thing goes to 0. So that tells us that 0 is twice the time average of the kinetic energy plus the time average of some xi fi. Okay, so that's the general result. Now, on the other hand, we're doing things non-relativistically here, So Fi is really partial V minus partial V partial Xi. So this equation then is 2 long-term time average of T is a time average of Xi partial V partial Xi. So we first said we're doing the virial of a non-relativistic bound system. The next thing we say is that V is homogeneous of degree n. But if it's homogeneous of degree n, bingo, Euler's theorem works, and we have 2t is equal to n mean value of V. So this is the virial, the non-relativistic virial theorem. So it's a combination of non-relativistic physics together with applied to a bound system for the case in which the potential is homogeneous in the positions of the particles, or the coordinates of the particles. And so the final form of it is then the T, long-term time average of T, is n over 2 long-term time average of V. Okay.
Can you repeat this again? Why does that go to 0? G of T minus G of 0 over T?
It's because G of T is finite, bounded, not simply finite, but bounded. And it's bounded because the X's don't get past, let us say, Neptune, and the P's don't get bigger than some maximum P, otherwise they'd escape the solar system. That's the idea. So, in other words, for a bound system, the virial is bound. So the time average is effectively the integral of G, the integral of the time derivative over time divided by the total time. In other words, this thing is integral from 0 to big T of G dot dt. And so that is G at big T minus G of 0. And then, because we want this to be the average, we have to divide by T. And so it's that. So this is finite, that's finite. This is bounded, that's bounded. This goes to infinity, you get 0.
Oh, we're taking the limit as T.
Yeah.
All right.
All right, so let me throw you a candy here. Good catch, good catch. Okay, so that's the Virial theorem. Now, Coulomb forces and gravity, oh, I can write Newton here. It's V is minus E squared over R, or V is minus big G M over R. So these are the nature of the particle. And what is this? This is minus E squared over square root of, let's just consider one particle for simplicity. X squared plus Y squared plus Z squared. So you multiply, you get a T squared, T squared, T squared, factor out, T squared becomes a T. So these are homogeneous, n equals minus 1. Because let's just review the definition here. This n, if it's 1 over T, it's minus 1. Okay. So in I guess I can't resist doing this example. Let's consider a hydrogen atom, our favorite example. Let's do it in natural units so we don't have H bars and C flying around. So then the energy is P squared over 2m minus E squared over R. The uncertainty principle says delta P delta R is of the order of 1 because H bar is 1 in natural units. I'm approximating that what is R. I'm going to approximate the mean value of P is 0, mean value of R is 0, 0 being the center of the where the proton is. So this is essentially RP. So then we've got a simpler expression here. We can say that E is actually P squared over 2m minus E squared P. And now you find that, let's minimize the energy. 0 is dE dP. And this is, the derivative of that is P over m minus E squared. So P is equal to m E squared. Let me make sure I've got everything right here. Yes. So then the kinetic energy T, P squared over 2m, this is equal to m e to the 4th over 2. The potential energy is minus E squared over R, but that is minus E squared P, since RP is 1. And P is ME squared, so again, this is minus M e to the 4th. And now what's the relation? The relation is P is minus V over 2. And remember, N is minus 1. So we've got, where's the general formula? T is minus a half V. And what we have here is T is minus a half V. So this is an example of the Virial Theorem. It also, by the way, shows you that you can estimate the ground state energy of hydrogen just using the uncertainty principle and some approximations here. And what you get is that the energy then is T plus V, and T plus V is just V over 2, isn't it? And V, if I've got V over 2 is minus M e to the 4th over 2 in natural units. Now, the way we turn that into standard units is we have minus M e to the 4th over 2, and then we imagine that salt is H bar and pepper is C, and we season this with salt and pepper until it tastes right. And when that happens, what we get is minus mc squared over 2, E squared over H bar C squared. Now, in the units that I've been using here, E squared over H bar C is 1 over 137. So this is minus mc squared over 2 alpha squared. This is alpha. And if you work that out, it's minus 13.6 electron volts. Zwicky, back in 1933, now it's almost 100 years ago, now let's say 70 or 80 years ago, he applied the gravitational Virial Theorem, which is essentially the same as this one, n equals minus 1, to his observations of galaxies in the Coma cluster. So the Coma cluster is a huge cluster of galaxies. He was watching these galaxies zip around, and I guess what he could do was measure the redshift of each galaxy, and that would give him some idea of what the, or maybe he could see the move, I don't know. I'm not an astronomer, God knows. And what he found was that he found that minus a half mean value of V, as estimated by judging how bright the galaxies were and estimating how much mass would produce so much brightness, he found that this was much less than T. And he could estimate T from how fast the galaxies were moving. And he said there's missing mass, and he called it dark matter. Current observations indicate that dark matter is essentially 5 times as much as ordinary matter in the universe. And so I've outlined 2 of the huge embarrassments of modern physics. One is that we don't understand dark matter. The other one is we don't understand dark energy. And the way experiments have been going with dark matter, it is very possible that somebody lecturing in the new building 30 years from now will be saying that we still don't know what dark matter is, and still don't understand dark energy. So
The building's gonna be done in 30 years?
what's that?
So the building's gonna be done in 30 years?
Unfortunately, I frankly don't have big hopes for the quality of the new building. I've seen the buildings UNM has put up over the last 30 years or 40 years. This building is pretty good because the person who supervised the construction was the head of the department, Victor Regener, and he was very smart and tireless, and so he made sure the contractors didn't get away with murder. He also made sure that the administration gave in to all his demands because he had dirt on all of them. And it turned out about 20 years ago, one of the deans was running a call girl service. This was after Reagan, okay, this was after Reagan. But there was, I'm sure, the equivalent, possibly worse, during Reagan's time. And that's why faculty in this department, in this building, have nice big offices. Reagan said, it's an experimental science. Every faculty member needs a laboratory. So we all have big offices with sinks.
I was going to ask about this, I don't know, concept of dark matter. So you're taking this time average? So is the reason why they think that there's, or the reason why people think of dark matter is because this Virial Theorem doesn't?
Yes.
And so, but you're kind of like taking, you have to take a time average. And so how long is this guy, how long did the person who did these observations observe this galaxy for?
Well, yeah, but the galaxy's been sitting there for 14 billion years. Well, say.
But I mean, if he's taking a time
least 10
average, that's
billion
something
years,
that
huh?
you sort. Well, if you're taking a time average, that's something.
Well,
that
yeah, all right, look, this is
just gather data.
okay, this is astronomy, okay? We have to make certain assumptions to do astronomy, and this is a reasonable assumption. Yeah.
In thermodynamics, average of time is the average of space. Is that a theorem?
Yeah.
In thermodynamics, the average of time is the average of space.
Well, what you're referring to, that's a good point. What you're referring to is that the time average is sometimes like the ensemble average. That's what people often do.
Okay.
Frankly, that's not always true, and so you should keep in mind there are 2 separate things. There's a time average of a system, there's the ensemble average of a system at a given time, and they don't need to be the same, really. In any event, there have been a gazillion observations in the last 70 years, and what you see in general is that there is much more matter then can be accounted for by the neutrons and protons and in other words, the atoms in the universe. And that seems very well established because it's been seen on various scales. It's been seen on the scale of a single galaxy as well as the scale of a cluster of galaxies. And it's built into the standard model of the universe, whereby the universe is 14 billion years, started with an inflationary phase, and then a hot Big Bang, and baryon nucleosynthesis, and this is all, and then the hot Big Bang left relics, which are photons that are now lower in temperature by a factor of 1,000 due to the expansion of the universe and the redshift and so forth. And it's all more or less consistent. Now, it could be wrong, but it's, you know, because we can't send a spaceship back in time and watch all this happen. And in particular, the inflation part could be wrong. That's the most speculative, but it's consistent with observations. And of course, then you could say, well, maybe the universe contracted, all contracted to very high density and exploded, and that was the Big Bang. Well, that's possible too, conceivably. Some people think that. I once thought that, wrote a paper on that. But anyway, I would say dark matter is pretty solid due to observations, and dark energy not as solid, but it's also there. And I mean, some people think, well, we just don't understand gravity. The trouble is, general relativity, apart from being very nice, really works well on a wide variety of distance scales. And if a replacement of general relativity I would be upset if a replacement of general relativity didn't include general covariance. That is to say that you can make the action remains the same when you change coordinates arbitrarily. And so I think of the theories that try to get around dark energy and dark matter by violating general covariance. I think those are crackpot schemes. But I could be wrong, of course. All right, we've got a few minutes left. Let me see if I can say something about, well, quickly, another example. Harmonic forces. V equals a sum mk omega k squared r squared sub k. Okay, so those are a bunch of harmonic variables. This is homogeneous with n equals 2, and so t is equal to v. So the mean value of t is the mean value of v. Okay, that's the harmonic case. Let's now switch to something completely different, namely all the things you can do changing variables. And I find this somewhat confusing. I think it's that when I was your age, I thought of changing variables as trivial, so I didn't really need to pay attention. Well, that was wrong. And so ever since, I've found changing variables a puzzle because I didn't pay attention when I was your age. Anyway, what's dA? Suppose A is a function of x and y. Partial A, partial x. dx plus, in fact, let me switch notation. A sub y dy. It's such a nice notation. Okay, so that's what we're starting with. We've got a function of x and y. But now what we can do is we can say, well, suppose we define v as a sub y. And then we define a new function b. What is this new function? Well, this new function is a minus Vy, so that's minus y, a sub y, or a minus v y. Okay, now we look for dB. What's the change in B? Well, the change in B is going to be ax dx plus ay dy, and then it's going to be minus vx y dx minus v, right? Because dy, just v dy, sorry. But now we said that v was a y. So these two terms cancel. So now we've seen that dB is a sub x dx minus v sub x y. Did I do this right? V sub x y dx. Yes, that is right. Oh, wait a minute. I want to do.
Why isn't there a derivative of v?
Yeah, I screwed up. All right. dB. dB is a sub x dx plus a sub y dy. That's the first term. And then we have this. Ah, yeah, I should have followed the notes. It's stupid of me to just wing it all the time. So let's redo this. So the rest of this is minus dvy minus v dy. But now v is ay, so these two terms cancel again. So dB is a sub x dx minus y dv. Okay. And yes, minus y dv. Okay. So now this gives the impression that b is then a v can be regarded as a function of x and v. But in order to make it a function of x and v, what we have to do is we have to take this equation and solve it for y. We have to be able to write y as y of x and v. And when we do that, we go back here and we say that b is equal to a minus v y, but y is this y of x and v. So now v is a function of x and v. Okay. And so I think that what we'll do, today is what? Thursday. What we'll do is next Tuesday I'll start this again. All right, any questions? And also, some of you probably asked questions and didn't get candy. Raise your hands and I'll toss candy. Okay, any further questions? All right, so I guess we can turn it off.